Hello everyone, myself Kajal Kumari, CSIR Research Fellow, working with Professor Mayank Goswami at Physics Department, IIT Roorkee. Today I am going to present my paper which is titled as Sensitivity Analysis of Calibration Methods and Factors Affecting the Statistical Nature of Radiation Measurement. Here is the outline of the presentation. So let me start the very beginning of this work. We have ordered sodium iodide thallium scintillator detectors in our lab, which is Divyadrishti Imaging Lab located at Physics Department, IIT Roorkee. My supervisor, Professor Mayank Goswami, asked me to set those detectors. I was aware about some methods which are frequently used to calibrate the detectors. When I have started to use those methods, I realized that those methods were dealing only with the calibration of voltage. Then what about the other parameters like amplifier, lower and upper limit of discrimination, energy window? I asked help from my seniors in department and observed that everyone was setting those parameters according to their own. Then I go through the literature survey and observe that no one have done this work. In fact, no one has mentioned. That was very good opportunity to us to find out the answer of some remaining questions. The motivation of this work is to find out the answer of some post-processing questions that required before the calibration of electronic setting of detectors, and at somewhere some of these are required at the time of calibration also. A lot of detectors exist at this time to measure radiation, but in our work we picked up the very basic and the mostly preferred for ionizing radiation measurement, which is sodium iodide thallium scintillator detector. The electronics of most basic detectors provide the knob or button, so we have control over those parameters. The questions raised related to the calibration and controlled by the experimentalist are: how many times or instances should one repeat an experiment? How long should one carry out a single instance of measurement? What values should one take: average, mean, median, mode uh, of the value of samples? What should be the optimal setting of the involved electronics? Which of the electronic settings are more important to pay attention to before one starts the experiment? Here is the methodology of the proposed work. At first, we set the values of the electronics parameters and then start the experiment to measure counts in the presence of radioactive source. In our work, we have used cesium-137. Then repeat the experiment to measure the counts at the same setting 30 times. Then change the setting and repeat the above procedure. 5 different methods: center limit theorem first, center limit theorem second, pulse width saturation method, true counts measurement method, and the gross method used to find out the optimal settings and the corresponding counts. By taking mean or median or mode of these counts array that we get due to repetition of the experiment 30 times, and the optimal settings are fitted into multivariate nonlinear equation to find out the parameters have major contribution in counts measurement. Let's come to the experimental part of this work. As you can see here, this is the experimental setup used to measure the counts. We have used 6 scintillator detectors, in which 5 of them are sodium iodide scintillator detector and the 6th one is cesium iodide thallium scintillator detector, which is coupled with the multi-pixel photon counters, photomultipliers. The experiment was carried out with semi-automatic, automatic and with manual bin. After measurement, to find out the optimal settings, we have used 5 different methods. The first 2 methods are based on center limit theorem, are used to fit the experimental data into Gaussian function, which are Gaussian curve fit, and the probability distribution function. In our work, we refer these as CLT first and CLT second. The third method is pulse width saturation method. This method uses optimality based on most flat or saturation region. The fourth one is based on the comparison of counts measured using sodium iodide thallium scintillator detector with high accuracy multi-pixel photon counter coupled scintillator gamma detector. And the fifth one is gross method. According to this method, the optimal parameter value has highest ratio of the square of gross sample count rate to background count rate. Using these methods, we have calculated 5 optimal settings from each method. Now, the next step is to figure out which setting is best among the calculated from 5 different methods. To figure out, we have chosen 2 methods. In the first one, we compared the counts measured using sodium iodide thallium scintillator detector with count rate of radioactive source. Among 5 settings, which gives relatable counts rate considered as best setting, and the method is considered as optimal method of calibration. In the second one, we have used gamma computed tomography, assuming that at optimal setting it gives the best reconstruction result if we compare to the other setting, if we compare at the other settings. From the results of these two methods, we have in our hand the optimal settings and the optimal calibration method. To know which parameters have major contribution in radiation measurement, we fitted the optimal settings and their corresponding counts in our modeled equation using multivariate nonlinear equation. We have modeled two equations, equation first and equation second. In the first equation, we have considered lower limit discrimination value, time, amplifier and the voltage, while in the second one we have considered number of instances as an independent parameter also. We have if you have noticed that we have mentioned that repeated the experiment that we have repeated the experiment 30 times, so we get count array at particular setting. To fit the settings into nonlinear equations, we need one value of counts. So three case arises: mean, median and mode of counts. We use these three statistical parameters to see its influence over accuracy and the precision of result. Now we are going to discuss the result of the carried work. The figure 3, it shows the counts detected by the 5 detectors at optimal settings calculated by 5 different methods. It was observed that the counts calculated by method 2, which is CLT2, are close to count rate of radioactive source. This is the geometry used for gamma CT system. We have carried out the experiment at the optimal settings calculated by 5 different methods and at random setting. But here we presented the results for the best method and at random setting. This one is the camera image of the object that we have used in our experiment. This one is its 3D image and this one is its digital analog. The bottom row shows the reconstruction result. This one is obtained by the projection data created using digital analog with 33.68% root mean square error. And this one is obtained at random setting with root mean square error 39.74%. And the last one is obtained at optimal setting with root mean square error 26.04%. Both methods, count rate resemblance and gamma CT, concluded that method 2, which is CLT2, as optimal calibration method. This is the result of the fitting of optimal settings of 5 detectors calculated by 5 different methods into multivariate nonlinear equation of 4 independent parameters. Statistical parameters mean, median and mode are also considered here. In these figures, we have plotted the entropy and the coefficients of time and voltage and the constant coefficient which is B9 coefficient. maximum entropy, minimum root mean square error, positive value of time and voltage coefficients, contribution of the constant coefficients smallest as possible, and the practical constraints based on human perceptions is applied to fit the optimal settings. Based on fitting criteria, we concluded that the method 2 is fitted best in the multivariate nonlinear equation. And our discussion also leads that the statistical parameter mean preserves the accuracy and the precision. It was observed uh, that average time has major contribution in radiation measurement. We have repeated the same data analysis by including the number of sample as an independent parameter and fitted in equation second, which we discussed in the previous slides. Entropy and the constant coefficients, which is B11 here, are plotted here, and from this analysis we found that the median optimized the result. Now we come at the overall conclusion of our work. It was concluded that the second version of center limit theorem is found to be the optimal calibration method. At optimal calibration setting, the gamma CT gives the best reconstruction result. The median is found to be the best statistical tool in our work if the sample size is included as an independent parameter during the calibration stage. Otherwise, mean as a statistical tool is recommended. It is concluded that the average time to count the radiation particle is the most important parameter affecting the optimal calibration setting. The value of the parameters obtained by fitting the optimal setting into multivariate nonlinear equations are given below. Here. For more details, one can go through this paper. Thank you.